Les dinosaures constituent l'un des sujets les plus populaires de la paléontologie. Il y a quelques décennies, un consensus scientifique est apparu selon lequel les oiseaux sont les descendants de dinosaures bipèdes et zoophages, connus sous le nom de théropodes. À partir de l'étude d'anatomie dinosaurienne la plus vaste jamais entreprise, une équipe de scientifiques a récemment suggéré que les théropodes sont plus proches de dinosaures herbivores comme le stégosaure, l'ankylosaure, l'iguanodon et le tricératops, qu'ils ne sont des herbivores géants à long cou, tels que le diplodocus, comme cela était pensé jusqu'ici. L'un des auteurs de cette étude, Matthew Barron, est mon invité pour cet épisode. Dinosaurs are one of the most popular topics in paleontology. A few decades ago, a growing scientific consensus emerged that birds are the descendants of bipedal, animal-eating dinosaurs, known as theropods. Based on the most extensive study of dinosaur anatomical attributes in history, a team of scientists has recently suggested that theropods are more closely linked to herbivorous dinosaurs, such as Stegosaurus, Ankylosaurus, Iguanodon and Triceratops, than they are to the giant long-necked herbivores, such as Diplodocus, as has been thought to be true for more than 100 years. One of the authors of the study, Matthew Barron, is my guest for this episode. So I'm thrilled to be here with Matthew Barron. Matthew, welcome to the podcast. So you're a PhD student in the Department of Earth Sciences at the University of Cambridge?
Yes, I'm currently a student at Cambridge and at the Natural History Museum in London.
Mm-hmm. And you specialize in the paleontology of dinosaurs. And
yes, yeah.
You were named in Forbes' 2018 list of 30 people under 30 to follow in the science and healthcare category.
Yeah, I was. Yeah, it was a huge honor.
Congratulations for that.
Thanks.
And so in the spring of last year, in 2017, you published an article in the very prestigious scientific journal Nature, the title of which was A New Hypothesis of Dinosaur Relationships and Early Dinosaur Evolution, in which you proposed a major overhaul in the dinosaur family tree. So maybe we can start from the basics for our audience. So I like to think that I have a little bit of knowledge, nothing at the specialist level, of course, but I like to think that I have some knowledge of dinosaur taxonomy. And so we can maybe explain the audience that for many decades, dinosaurs have been classified in two major groups. There is Sauriskia and Ornithischia. And the first name means lizard hips, and the second name means bird hips, respectively. So maybe you can elaborate a bit on this sort of classic taxonomy tree of dinosaurs.
Yeah, so in 1887, a British paleontologist called CelestiC looked at all of the then known specimens of dinosaurs. There was maybe 10 or 12 species. Possibly a few more by that time. And he looked at features of their anatomy that they could possibly group them on. So lots of people had put forward ideas of how these animals should be grouped and what the taxonomic names should be given to various groups. And what CelestiC proposed as his big idea was it was largely to do with the arrangement of the hip bones. So he spotted that some dinosaurs have hips that are much more reptile-like in the way that they're constructed, whereas a small group had hip bones that were similar to birds, although he sort of recognized that this was a coincidence, this is coincidental similarity, what we call convergent evolution. Mm-hmm. And he noticed that these two groups, there were other differences between them as well. And so, yeah, he grouped them as these lizard hips and these bird hips, two groups. And so the lizard hips are sort of long-necked tree browsers like Diplodocus, as well as big meat eaters like T-Rex and small meat eaters like velociraptors. They were all grouped together. And then the other groups of herbivores that we know of, like Triceratops and Stegosaurus and Parasaurolophus and whatnot, they were all put into the bird hips group of dinosaurs.
Yes. So it's also a fact that birds themselves, I mean modern birds, are known to descend from dinosaurs, or we could even say, maybe in the strict sense of the term, that they are dinosaurs themselves. And they are member of a group called Theropoda, which back in the days of the Mesozoic era featured these bipedal flesh-eating dinosaurs. So for instance, the ones that you mentioned, Tyrannosaurus or Velociraptor. And so the catch is that under the old, or the sort of widely accepted classification, this group Theropoda, to which birds belong, is a subgroup of the Sauriscia group and not of the Ornithiscia group, which means that birds descended from dinosaurs that are said to have lizard hips instead of bird hips. And I'm wondering if this was a source of major preoccupation or confusion, if you will, among paleontologists in recent decades.
I think, yeah, like you said, they're sort of counter to what you might think that, yeah, the birds under the old scheme of classification would come from the lizard hips group, and like I say, it was always recognized as a convergence, and Seeley and people at his time didn't think that birds descended from dinosaurs at all. Obviously, like you say, what we now know is that you're right, they are in fact actually dinosaurs. Technically speaking, they do belong to the group, but it's this lizard hip group, and at some time in their evolution, for one reason or another, it's probably related to becoming a herbivore and changing what you eat. They rearranged their hip structure in the same way as the bird hip dinosaurs had done many millions of years before. So it did cause a little bit of I think confusion. Lots. I think some people quite often make the mistake of assuming that they must belong to the bird hip group, but yeah, you're right, they don't.
Well, did it motivate some avenues of research, this sort of counterintuitive taxonomical facts? I mean, did people say, it's not really natural that birds would belong to the lizard hip group instead of the bird hip group? And did they try hard, if you will, to make that fall back? I mean, change in one way or the other the classification tree to make things more intuitive in a way.
There are several actually in the history of dinosaurs. This evolution of the rotated hips, it occurs in birds. It also occurs in therizinosaurs, which were another group of theropods. I think we know, but there's so much evidence that birds descend from theropods, and that early theropods are saurischians, that it never. There's lots more that unites birds than just the problem of the hips. That that's outweighed by the huge body of evidence that suggests that birds do descend from one lineage of theropods. There are a few people who may disagree with it, but the argument's done now from a scientific point of view. And I think, but certainly in terms of why that characteristic changes so much is something that should be and hopefully will be investigated more, particularly in light of our sort of new proposal too.
So about this new proposal, so you proposed this new classification, in this Nature paper last year, and so in this classification, Theropoda, the group of flesh-eating bipedal dinosaurs, which includes birds, by the way, includes Ornithischia to form what you called Ornithoschelida. And so this means now bird legs in Greek. And with this new classification, birds would finally, so to say, rejoin the group of dinosaurs said to have bird-like features. And so, yeah, maybe this is a question that will, resonate a lot with what we already discussed. But leaving aside the evidence that you put forward and the detailed data that you used to defend this new classification, did you have the impression that this the fact that under your new classification, birds would come once again within the group of dinosaurs said to have bird-like features, was it a way? I mean, was it something that seems persuasive to paleontologists?
When I started the project, I wasn't sure what to expect of the outcome. We were just sort of assembling the big data. But yeah, there are, like you say, there are some nice sort of side products of this result, this rearrangement. It does bring the group where we see lots of these bird-like features, closer together. It reduces the number of assumptions you would have to make about when certain things appear, including things like feathers, because we have ornithischians with a feathery-like covering, like Calindrodromeus, for example, and we also obviously have feathers appearing in somewhere in the bird theropod lineage. And this again, could this new arrangement suggest maybe it is something unique to that group? The ornithiscalidae group might not just be linked by features of the legs and the hips and of the grasping hands and all the other features that we pulled together in our analysis, but it could also be things like feathers. It could be things like metabolism and maybe the big long-necked tree-browsing types like sauropods, which they aren't related to these other two more closely. Maybe they are actually the ones that are much more primitive and reptilian in most of their ways, don't have feathers, maybe weren't such a high metabolism. And so maybe, we've changed the point at which lots of bird-like features might have first appeared on the branch.
Okay. So what type of data did you use actually to build this classification tree?
It was sort of morphological data, so taken from the skeletal anatomy of the specimens that we looked at. So we gathered lots of data on specimens that we visited in museums and that we collected, and we took measurements and observed whether certain bones had certain features. And for a large number of the species we were interested in, we basically compiled this big list. I mean, there was obviously not all the specimens are complete, so there's missing data in there, but we got as good a sample as ever has been produced before by a long way, and put lots and lots of data in. So yeah, it's hard anatomical evidence from the preserved skeleton. Unfortunately, we don't have soft tissue for soft tissue characters or even genetic material. That's all unfortunately far too old to have been preserved, which would be very helpful. So all we have is the anatomical stuff from the skeletons.
Okay, so then you use these skeletons and you sort of describe them quantitatively, and you see what looks like what, and you build this family tree.
So we built the data set over the course of 3 years, taking lots of measurements, and then what we have is essentially at the end of that a sort of large table, which is sort of like an Excel spreadsheet, and where each species is sort of marked or scored for this feature. Does it have it or not? And yes or no, or unknown, or has state 1 or state 2 or whatever. So each species is essentially turned into a unique code, kind of like a binary code or a barcode, where we can then use software to compare those codes. So each species is reduced to a string of numbers based on what we've observed, and then we get the computer to work out, using different parameters, different types of math, what kind of family tree is the most probable given what we know about evolution and given what we've observed of these specimens.
So to clarify once again for the audience maybe, but I don't know, maybe this will inspire you to add something. So under your new classification, the sauropods, so the usually long-necked plant-eating dinosaurs find themselves sort of on their own in the CelestiC group, so that is in the lizard hip group, with a smaller group of herosaurids, which happen to be carnivores, but they are not, the sort of classic usual group of carnivores. And then you have the other group, which is Ornithoscelidae, and these these are the theropods, so which feature the bipedal flesh-eating dinosaurs of back in the days, and today the birds, and as well as 3 other big groups of plant-eating dinosaurs.
So that's essentially right. That traditional group of putting the traditional idea of putting the big meat eaters and the long-necked herbivores together was scrapped in our scheme, and the long-necked herbivores were left pretty much on their own in what remained of CelestiC. They were still joined there by one one small collection of early carnivorous type predators from the Triassic of South America that we call Aerosaurs. They're a very odd group of animals. They've moved around a lot in the tree. No one's quite sure what they actually are. Some people think they are dinosaurs, or some people think they're not. Some people think they're theropod dinosaurs. Some people think they're not. They've moved around a lot. So they remained in the CelestiC group with the sauropods. But they essentially happened was the theropod group, which have always been also in there with them. We moved those out and paired them up based on lots of similarities with the ornithischians, which was entirely sort of a new proposal.
Although it had actually been proposed a long time ago by Huxley.
Yes. Right? Well, so once we got this result, we had not seen it in any modern literature, and certainly no analyses had produced that idea. But what we did do is we went back through all the old, before CelestiC, all the other ideas that people had put forward for some of the animals that they'd seen, and tried to group them together. And we found that Huxley had named a group that contained only theropods and ornithischians and didn't contain any sauropods. So we thought, perfect, that fits. That's an idea that Huxley floated in 1870, but it was not really listened to, and CelestiC's idea really came to the forefront after the 1880s and just stuck ever since, really. And this old idea of ornithiscalida just dropped off and was forgotten about. So it was quite nice to find an old name for it.
Yeah. So what has been the response actually to this proposal by the specialists, by the paleontologists? Have they been mostly convinced? Have they been more resistant to this new proposal?
It's been a mix, actually. I think initially it was surprise because we really didn't tell many people about the results we were getting until we published them. And then I think after people took time to think about it, a lot of people said early on, like, yes, it makes, having seen specimens and things, it makes a lot more intuitive sense. So, people were happy to see it challenge the old ideas, and it's good to have that refreshing view. I think other people were less keen. Some people were very sort of convinced of the old model, and some people have done a lot of work on the old model, and they had data to suggest the old model was right, and so obviously naturally wanted to test our idea. So it was a mix of some people, and lots of people, even if they didn't necessarily believe it, were just interested to see that such a big data set actually produced uncertainty rather than, it challenged an old idea that we were so sure on. So it was a good reaction. But I think obviously with science, these ideas, you need to keep testing and retesting. I think people will. Certainly the nature.
And what's your current opinion, if you will, on the status of this proposal? Did you do further work in this sense? Do you think that maybe you collected some new data, or you found some new way of analyzing the data that either confirmed or fragilized this?
Yes, we took the data. Luke Parry and Jakob Winter and I had a follow-up paper in Royal Society Open Science, where we essentially took my data set and other sort of early dinosaur, versions of early dinosaur data sets that had been handled by other people, and we made some changes too, and we ran it through different types of analysis, basically. So rather than just parsimony, we also did Bayesian maximum likelihood and Monte Carlo Markov chain, which are different ways of assessing data, and it makes different assumptions, and it applies different rules. What we got was, using my data set, we got support for the ornithiscalida hypothesis, which was quite nice.
Yeah, that sounds pretty good. I think that there was a fairly big paper that challenged yours, on the other hand, but
so
there was this study in November. I think it's the study by Langer.
Langer et al. So this big group got together after our paper came out, almost immediately after it came out, actually, and they really were determined to test it as best they could and look back into the old ideas and see where there would be disagreement and could they break down our result. They were really, I think, determined to challenge us and to really test our hypothesis. So they initially, I think they ran an initial set of analyses using Bayesian and things, obviously got the same result we did in the Jakob and Luke paper. But then I think what they then decided to do was, well, we can go in and change the data itself. So they then took my data set and they made their own version. Well, they didn't make their own version. They took mine and then they reworked the key specimens, how they were scored. And, like I said before, we looked at specimens and we scored, did things have this? Didn't things have this? They went and did that themselves based on their own interpretations of what the physical characters mean and their own interpretations of what the skeletons actually show. And eventually, after a while, they changed about 10% of our data. And then they ran an analysis that got a different result that didn't recover the Ornithoscelida model and actually recovered the traditional Ornithosauruskia. Yeah. But they only got it to the point where it was only 2 steps short. So that is the changes that would have to happen in the tree to get that tree was only 2 steps fewer than it would be to produce an Ornithoscelida hypothesis. So that's only of the 10% of the data they changed, which is about 3,000 characters. Only 2 of those changes would have to be mistakes by them or incorrect or to go the other way to get the old model back again. So while they challenged us and they claimed that they'd managed to break down the result, they actually really hadn't. It was not statistically significantly different to our result at all. What actually their work showed is that even if you completely reinterpret everything as best you can to get the old idea back and really try and work it, you can't make it stick, which is also interesting. There's like that uncertainty right at the base.
Yeah, so it was two steps that they changed out of how many to give us an idea of the relative.
The original data set.
Importance of this manipulation.
It was the original data set was 30,000 data points roughly, and they changed about 3,000.
Yeah. But you also said that no, I misspoke. It wasn't that they changed steps, but had they changed a few. I mean, you mentioned these 2 steps. Had they changed them in their analysis, this would have. This would have seen them recover your new proposal, and I'm wondering. How big a change that is, these 2 steps changed in the analysis of the data.
Well, it's nothing at all. And these trees are thousands of steps long, naturally. Just there's thousands of changes occur as you move the tree, and you would only need to assume that 2 of those changes were incorrectly scored in their revised data to reproduce our tree. So it's really not significant at all. It's a very small difference, and what exactly those differences are, it's going to take a lot of time to go through and figure out where we disagree and why we disagree. But it's entirely possible that in their fervor to recreate the old model, there's areas where I would say that they've looked at something in a certain way, or they've changed something in a certain way to make the data behave in a certain way, and I don't think it would take a radical reworking by me to get our old idea back again, and for me to feel very confident that that is still correct.
Well, that's it's interesting. So it looks like the new classification is a bit more solid at the moment, but it seems that the whole thing is it's on a knife's edge almost. At least that's what it sounds like. It is.
Yeah, I feel confident in it. I think it makes more sense intuitively to me as well. And I think also just now that we're learning more and we're finding more specimens, I think hopefully with time the balance of evidence will tip away from, because I still think it's just absurd that we are so desperate to hold on to the traditional model. It was proposed by someone in the 1800s who didn't believe in the process of evolution, that grouped animals based on a small number of Jurassic and Cretaceous specimens that he had some access to back when we didn't really fully comprehend what they were, or the concept of deep time, or like natural history in the way we comprehend it now. And to think that fundamental dichotomy has to run all the way back to ancestor number 1 of all dinosaurs, and the split occurred on that day in the Triassic, right at the beginning. It would be a madness if that was actually true. It must be more complex than that, and I think that hopefully we're building a better picture as we find more stuff and get better at analyzing stuff.
Well, let's hope so. It's very interesting. I will try and follow this to the best of my ability. I have another question, which is not related to your work directly, but I was wondering if you could point the audience to some reference work, for someone who would not be a specialist, obviously, but who would like to become acquainted with the latest developments in dinosaur paleontology and to have, a broad but still rigorous overview of the current state of the knowledge. So I don't know if you're familiar with this book, but in the 1990s, my parents bought The Ultimate Dinosaur book by David Lambert for me. And I read it a lot. And I don't know if it was a very good science book, but certainly it was up to date in that it mentioned that birds were dinosaurs. And I was wondering, if you know of some book today that can take the non-specialist and teach.
Yeah, no, there's several. Yeah, there's several good ones. I think The Ultimate Dinosaur is actually getting updated. There'll be a new edition of that coming out soon with lots of revised stuff, I believe.
Mm-hmm.
There's this also now coming into its third edition soon is The Dinosauria by Champel, which is a sort of large, quite heavy, but it's everything you need to know about all the major dinosaur groups. But a good starting point, I think it's also partly one of the things I read early on in my studies to get familiar with it, and I think it's good for anybody, general audience-wise. Steve Brassati wrote a book called Dinosaur Paleobiology. It's part of a series called Topics in Vertebrate Paleontology, and it's very, very good introduction to everything, and it's fairly up to date, and it talks a lot about how the classifications were originally thought about, but also in much more detail within the groups, and it gives another sense of what science can do today and how the field's moved on, and it's good for learning anatomy from it. I'd say that's a good start for anyone interested.
Okay, that sounds good. Although you might be, you might argue that all these books might need to be revised somewhat in the wake of your new proposal. I mean, if it becomes accepted by your colleagues.
True. I mean, it's going to be even if they just include it to say there is this other possibility. I think they are going to have to be updated. We're not going to be able to get away from ignoring it, which is quite nice. I've made a bit of a change and caused a bit of a stir. But hopefully the literature that in the next few years will, reflect the fact that we are at the verge of sort of having to admit we don't know as much as we thought we did. And it's been really interesting to be involved in.
Yeah, certainly sounds exciting. So I have one last question for you, which is probably outside of your area of research, but I'm just wondering what the current status of the knowledge on dinosaur extinction is, because this was when I was reading these, books for kids, not all of them, but let's say for the general public in the 1990s and maybe into the 2000s, it seemed that people were putting forward hypotheses. Of course, there was the meteor hypothesis, there was the volcano hypothesis, there were even some hypotheses based on new pathogens that might have wiped out the dinosaurs, except for the birds, of course. Is it true? I mean, I think I sort of understood that the meteor hypothesis has become very solid. They are now quite confident that this crater in Mexico is the sign that there was this huge meteor crashing into the Earth around 65 million years ago, and that's what caused the dinosaurs to go extinct, except for the birds.
I mean that's generally held by most scientists to be fact. Now that's probably very, very likely to be the main cause of the global mass extinction that we see at that boundary. There's some people that say that it might have been a double effect, that the meteor itself might have also been involved in triggering large lava outpourings in other parts of the world, and that maybe that's linked. It's obviously exceptionally hard to prove that because it's huge time, a long time ago, and how do you prove that? But there is some argument that some dinosaurs were already perhaps in decline just before the event, but I also don't think the evidence is strong enough to support that idea yet. But the meteor certainly was the main factor, and I think most scientists would agree on that now.
I see. Okay, so
seems to have moved forward pretty quickly in knowledge on that point, because as far as I could, understand, 20 years ago, it was really not very clear at all.
Yeah, it's amazing how quickly things have changed. Yeah, and the confidence to which we can say now that birds are definitely part of the dinosaur lineage, and we are getting better at most stuff. Our understanding has become pretty good.
Mm-hmm. Well, listen, maybe your hypothesis, I mean, it's not a hypothesis, but your proposed overhaul of the dinosaur family tree will one day, come to pass as generally accepted knowledge by paleontologists.
Hopefully that would be wonderful.
One can hope. Yeah. I mean, I don't really have a dog in this fight, but yeah, I'm just curious of what will happen. Yeah.
Maybe.
Would you like to add something, Matthew? I mean, I asked all my questions at this point, so I don't know if I missed something.
I think we covered all the bases pretty well, and you seem knowledgeable, and I'm sure your audience will appreciate the sort of clarity on a few points. So I just thank you for having me on. It's been really interesting. See, sort of, it's nice to see that so many people are still interested, and how much public interest as well as academic interest this has generated. So, yeah, it's cool.
All right. Well, thanks a lot, Matthew.
No problem.
All the best.
Yeah, you too. Take care. Have a good day.
Yeah, good luck convincing your colleagues.
Thank you very much. Yeah, I'll do my best.
All right. See ya.